The floor system used in a school classroom consists of a 4-inch reinforced stone concrete slab. Sketch the loading that acts along the joist BF and side girder ABCDE. To solve this problem, first of all, let's see. This is a one-way or a two-way system using our ratio, length of the joist divided by the span, 3. This is greater than 2, therefore it's a one-way slab system. We can proceed with the dead load calculation now. So this slab, concrete slab, is a stone concrete slab with 144 pound per cubic foot, and it's 4 inches thick, and the load that our joist BF will be holding would be 5 foot on each side, all equals to 240 pardon me, it's 10 feet. All of this is equal to 480 pounds per foot. Now our live load for joist BF is, for using our live load table, we know that this is a school classroom, so it'll be 40 pounds per cubic foot times the load that our joist will be carrying, so it becomes 400 pounds per foot. Adding these together, we get our total load. That's 880 pounds per foot. Now we can draw our free body diagram of the joist BF. And we know that our uniform distributed load for this joist is 880 pounds per foot. And now we can find our point load, which is going to be 880 times the length of our joist, which is 30 feet. It comes up to 26,400. And this point load will be located in the center of this joist. Now we simply need to divide this load by 2 in order to find the load being exerted on each joint of this joist. And this comes up to 13,200 pound, and it will be located on B and F. Okay, now we can proceed to our next adventure, that is to find the loading for girder A to E. Let's draw the free body diagram of the girder. It'll be A, B, C, D, and E. B, C, D are all symmetrical, and we already found the load for B. So we can simply copy this load value to our point loads C and D. And looking at the diagram, we know that our point A will be half of whatever our point B is, because the area that is being loaded onto the joist A here is only half of what we had for joist BF. Therefore, 13,200 divided by 2 is 6,600 pound. And this will be our point load for both E and E. Now, what happens if we change certain values? In this case, our value for our joist length, I'm going to change it to 50. Let's see if this is a one-way or a two-way load system using our ratio, where joist length is divided by our span, and it's 1.5. 1.5 is less than 2, therefore it's a two-way slab system. Okay, before we proceed, let's draw the free body diagram of the whole structure. And from our lecture on tributary loading, we know that the loading for two-way system is distributed in a triangular pattern towards the girder and then trapezoidally onto the joist. And the angle between the corners is 45 degrees. So for example, for this joist BF here, the area shaded in red will be handled by the joist, whereas area shaded in green will directly be loaded onto the girder and won't affect our joist. Okay, let's do the dead load for joist BF. Our dead load for concrete stone slab is 144 pounds per feet cube times the thickness. 4 divided by 12 makes it foot times the loading that would be carried out by our joist, which is 10. Solving this, we get 480 pounds per foot. And for live load, we're going to have a similar value as our previous example, but we're going to solve it here. So it's 40 pounds per foot square times 10 feet. That's the load our joist going to carry from the slab. And this is equal to 400 pounds per foot. Adding both of these together, we get total load of 880. Before we proceed any further, let's draw the free body diagram of our joist BF. Our uniform load for this joist is going to be trapezoidal, and it's going to be the peak. This load is going to be 880 pounds per foot. Now let's draw our free body diagram for the girder A to E. We're going to have point load at B, C, and D. And because it's a two-way system, we're going to have triangular loads in between the point loads, because some of the roof loading or the slab loading is going to be directly transferred over to the girder. Before we do our point loads for this free body diagram, we're gonna calculate our peaks for these triangles, and all these triangles are the same height. I know I've drawn them non-symmetrically. We can find the peak of these triangles either using the harder form method or the easier method. I'm going to try to use the harder method. This point here is halfway, therefore its length is here is 5, and we know this angle is 45. Solving for A here, I'm going to highlight here in red. We have 10 45 equals to A divided by 5. Solving for A, we get A is equal to 5. Now we can use it to find our dead load, which is going to be 144 times 4 divided by 12 for our slab thickness times the highest amount of times the width of the slab that's going to exert the load onto the girder, which is 5. Solving this, we get 240. Now the live load, which is 40 pounds per foot square times 5, we get 200. Adding these together, we get our total load, that's 440 pounds per foot, and that's our peak for all these triangles. And the easier way to solve the same value is simply dividing our peak load for our joist BF, and we'll get the same value. But I just wanted to show this in the problem as well. Let's find the point load for B. Well, first of all, let's transfer our point load from joist BF, and we know that whatever our point load for B is, it's also going to be same for point C and D. So point load for BF is going to be 2 times area of a triangle, half times 880 times 5 divided by 1045 plus area of the rectangle in between. So that's going to be 880 times 5, all equals to 0. Well, all equals to our solution 8,800 pounds. So our point load here is 8,800 pounds. Dividing this by 2 because our load will be distributed between the 2 points B and F, we are left with 4,400 pounds on each point. Therefore, our point load here for B is 4,400, 4,400, 4,400. And now we have to include our point load from these triangles here that is being exerted on the girder as well. And let's convert this into point load. So we have 2 times area of triangle, which is half times 440 times the distance, which is 5. Solving this, we get another 2,200 pounds added to our 4,400, and this becomes to, well, I'm going to rewrite this, 6,600 pounds. For our points at E, we're going to have half the load from our whatever our point load was for joist BF, which was 4,400 divided by 2, and then half of the load from this triangle here, and that's another 1,100. Adding both this together, we get 3,300 pounds as our point load for point A and E.